time's almost over. Okay, so if we consider this, then we can take a Taylor series, right? So what happens? We get f of q plus q dq f of q. So I need a bracket there actually. Just d dq f of q. So that's like to the first order, and so we're saying that. Right, epsilon is some small number. Okay. So for small numbers, you're probably familiar with like Taylor series. Near the point at which you're approximating, it's very, very close, right? So let's say we want to repeat the scaling. Well, what could we do? First of all, let's factor out f of q. So we get 1 plus epsilon q d dq. Okay. So this notation is very common in certain physical sciences, in physics, and also in engineering. So by Oliver Heaviside, he would just call that capital D.
Differential operator.
Differential operator, exactly. So it acts like a multiplicative term. So to evaluate this, you multiply it out, but it's not abelian. So non-abelian means you can't, AB does not equal BA, right? Because this is operating on everything to the right side of it, okay? Now, we want to apply maybe an arbitrary scaling, not just by some infinitesimal. So let's just apply it a second time. So let's consider like a new q prime. This is not a derivative, this is just a new variable. And let's say that that's a scaled version of q. And so if we consider the differential of q, we just multiply it. The factor in front stays the same. Okay. And now we can apply it again. So here I'm going to write out all the steps. It's kind of laborious, and you don't normally do this because when you get used to working with these operators, you kind of get used to the form. You can skip a lot of it. But for the first time out, I think it's handy. So that's just substitute this in. Right? And okay, so where's that from? That's from right here. So using 2, so 3. I'm just using the same notation as in the notes. So there's some skipping one. Okay, so now if I substitute in my q for q prime, then okay, and now the 1 plus epsilons, they cancel, right? So and now I'm going to go ahead and evaluate this one again, which is going to give the same term, right? Can everyone see that? This is this right here. So we substitute this in to get to f of q from f of 1 plus epsilon q. So then we get okay. So now we've applied the scaling twice, right? So we nudged it a little bit by an infinitesimal amount twice. Now, what happens if we do it an arbitrary number of times? Well, if we apply that infinitesimal, 1 plus epsilon scaling n times, then we get okay. For the same reason, you just go through this, you iterate through this, and you're just going to accumulate powers over there. So this is a true statement for any infinitesimal epsilon. So we can actually choose what we want our epsilon to be. It's, the criteria is just that it's, greater than 0 and much less than 1. So let's say where so the reason why we're choosing this particular value is because we know that e to the lambda limit and we know that this is true because of that identity down there. There's a proof in the first page of your of the lecture notes. It's a very elementary thing, but what we're trying to do is match forms. Right? We want this to be in a form that we can work with. So if we take this equation and we apply, that choice of parameterization, then we can let n go to infinity so that we get that e to the lambda over n. Then we get a limit as n goes to infinity of f 1 plus lambda over n all to the power n of q. So this is the scaling by any arbitrary amount, because we can make this depending on what we choose for this number. We know that that's e to that power, right? So we can actually make this go to any number we want as n goes to infinity. We just have to choose which number we want. So then that is going to be equal to the limit as n goes to infinity of 1 plus lambda q d dq all over n and q. Okay, so now let's write it in a simple form that we can sort of recognize what's going on. We can start using the identity that we have. So we get e to the lambda q equals e to the lambda q d dq f of q. Okay, so if we just say, okay, our k, now we don't really need that lambda there. We can just say k is equal to e to the power lambda, which we can make any value. Then that implies our lambda, what we were calling lambda, is actually just the log of k. So lambda is log k, and this is now a way to scale by any given amount, and it gives you a recipe for how to do it. So now let's define that as an operator. We can sort of work with it a little. So looking at the form of that, we'll say, okay, well, which part of it is doing the scaling? And it's pretty clear that, you know, our untouched f of q is here, and this thing is doing the scaling. So let's just call that s and parameterize it with a k. And because we have this relationship here, log k. So we can say, okay, well, that's equal to okay, so this is an operator, and by that I mean it accepts a function and it returns some other function. And if we had a arbitrary function h of t, and we apply sk to it, well then it's going to equal h of kt. Okay, so this thing, this basically embodies a Taylor series, right? Because of the definition of the exponential, how we would actually evaluate this is by evaluating that Taylor series. And so you've got derivatives that are applied to each term as you expand that Taylor series. So formally, S of k is sum log k and so this is what the formal definition is. However, the higher order derivatives, they turn out to not actually matter. And I will show that to you, not prove it to you. It's something to do with these operators on left invariant fields. But we'll now apply this operator, or try to the problem. Yeah?
Should that be diode q after log k on the second line?
Here?
Yes.
It should be, oh, q. What? Yeah. Yes. So now we have a way of getting from an f of q to an f of kq just by applying this. Can anyone tell me what will we do to go the other way around? So right now we have skf equals f of kq. How do we get from f of kq to f? Any ideas?
What's the inverse?
Do you
Yeah.
just take the logarithm
Nope.
since it's exponential?
So let's just say, yeah, what's the question is, what's the inverse, okay?
Yes.
So the inverse is the thing that undoes this. Well, what this did was stuck a k in here, right? So what would get rid of that k?
You get it outside.
Or what would undo it?
What would undo the thing? This stuck a k inside. I want to undo that. So
Multiply with a k factor or
multiplying by k would give me k squared.
no, outside.
How do you undo multiplication by k?
Like,
Yes, 1 over k, exactly. Right? So if we apply this 1 over k operator here, on this side we get s 1 over k, s k, f. These two just cancel. And on this side, we get f of 1 over k, k, q, which equals f q, because these two cancel also, right? So now we actually have an operator that, given an f of kq, gets us an f, right? It unfortunately requires an infinite number of derivatives and whatever, but we do have a way of writing it down. So usually, if you look at in like physics, in terms of like translation operators and stuff like that, they're all parameterized without this log, okay? And so, you know, if you had a k here, you'd have a negative k as the opposite operator because they're working in a multiplicative space. But that's not convenient for us. We want the log k, so we parameterized it this way, so it's 1 over k, right? We make the multiplication visible there. So s of 1 over k is the exponential of negative log q, oops, q d dq. Okay, so that's the definition of the inverse. And now we're going to apply it and see if we can get a result. Okay. So we have f of q is 1 over k g k. So you know, at the outset, I got to say that this is for analytical g functions. So they have to be analytical in k and f, so you can take derivatives. Now this is true for all k greater than 0, right? This expression. That was our assumption early on. So we're going to choose k equals 1 plus epsilon. You know, if we put 1 in here, right? If k is 1, well, g of 1 comma f is exactly the same as f, right? Now we're just going to choose, instead of 1 plus epsilon. So then we get f of q equal to.
And this is the infinitesimal. This is like why we like those really big rings of lights with large numbers of lights around the ring.
Q d dq g 1 plus.
Professor Rand.
Okay, thanks.
I might be anything because my next class starts in.
Yeah, for those who
Oh.
have another class, feel free to roll along. It doesn't look like we're being evicted, so maybe we can go a little over if we want to.
Okay, so then we kind of get to somewhere, some simplification. 1 plus epsilon minus q d dq. Okay, so now we've got this far, and we want to evaluate what this derivative actually does. So we use the Taylor series about 0, just the first order term, and we evaluate that. And so we get q equals g.
Yeah, for the benefits of those who have other class, I'll post this too, so you can see the rest of it. Because this is really phenomenal. This is a really amazing piece of breakthrough research.
So we're expanding a Taylor series about epsilon. Okay. So we take the derivative, so we have to subtract 1 there. And then there's g 1 plus epsilon f. And now, the second term here is going to be so because k is 1 plus epsilon, then dk is d epsilon. Yeah. So we'll just write d epsilon here, there. So Now this is evaluated. So remember when you're taking a Taylor series or a Maclaurin series, this part is actually evaluated at a certain value. So that's what we're doing here. Percent equals 0. And also from here, you can see that if epsilon equals 0, then k equals 1. Right? They're the same thing, because we want it in terms of k. So then we get G1 F plus epsilon negative Q D dQ. And now this is 0, so this is gone. This whole complicated term is just gone. And we're left with G1 plus epsilon F. Correct? Yeah. And plus D. Now, we've said k is equal to 1 plus epsilon. Well, we can just do the reverse substitution and put k back in. Right? And the differentials are equal. Okay, so now what have we done? Well, we've got f of q in terms of g, but this term is simply f, right? Correct? Yeah. And this term, because we are evaluating at epsilon is 0, this term is also f here. So we get, well, if we subtract off, so this is f and that's f, and just write 0 there, is equal to, what's in here? This is negative Q d dQ of f plus dg dk. Okay, so now at least we've got an expression that has f, has a q in it, and it has the g, so we can just finally write a simple answer. So we look at that and say, okay, we'll take the negative f quantity to the other side and divide by q. So then we have df dq is equal to 1 over q dg dk, evaluated at k equals 1.
So this is a really amazing result here. This allows you to really turn any comparametric equation into an ordinary differential equation. This is a really phenomenal piece of work here.
So this is the final answer that we get.
Big round of applause for Adnan here. Yeah, this is just amazing.
So you'll notice that we took a Taylor series to derive the scaling operator, and we only took one term. We took another Taylor series to estimate what the result is, and we only took one term. So maybe we should just very quickly check, does that actually make sense? And if you look at the original definition, and this sort of solves the whole thing, if you just look at this and say, okay, what if I take a derivative with respect to k on both sides and evaluate it at 1? Because I'm always allowed to do that, right? I'm always allowed to evaluate wherever I want. Then I get dg dk evaluated at k equals 1 is equal to q. Now I have the total derivative, so f prime of kq evaluated at k equals 1, which is just q f prime q.
Yeah, isn't it amazing
So
how
that's it.
How
So
beautiful and simple this thing is. Such a profoundly wonderful
you
thing,
just
but
take this over here, and you got your 1 over Q, dg, dk, evaluated at k equals 1.
it's amazing how obvious it is. It slaps you in the face, but on the other hand, nobody saw it for years and years. Like there must have been 20 years gone by, nobody.
So this is an ordinary differential equation. It's always separable because, as you saw, the q just comes over here, and you can just integrate both sides, right? And you know, there's an example in the lecture notes. I think we should cut it short, but it's very, very straightforward to apply this rule, assuming that you know what an ODE is. So separable ODE. So if you have dy dx equal to fx g y, well, this is separable. So that is always easy to solve. Implies that integral of fx dx. Yeah. So in the last page of the notes, I work out an example, which you can take a look at. It's very, very straightforward. There's none of this like crazy, differential operators and whatever. It's just, hey, let's apply this directly. Give me a g, I'll give you an f. And some parameters come out of that, some constants for integration, whatever. But it's very, very straightforward. So now you've got a recipe, and because we verified this result here, that means that that whole derivation actually gave us the exact answer. So that's it.
Yeah. This is really amazing. Like you can take any comparametric equation and bang, just turn it into something that's solvable using ODEs. So this is like really a very profound result that's a really important contribution to science across many disciplines, because comparametrics applies to so many different things where you can sense and measure. Like if you can't measure, you can't get in to measure something. You can't get measuring instruments. You can learn a lot about something by comparametric analysis. So it opens up a whole universe in medical imaging and all kinds of systems analysis, and there's just so many use cases for it. I think the profoundness of this contribution, I think, will be recognized in years to come as it starts to revolutionize the world.
All right, well, are there any questions? No. Okay. Have a good one.
It's crystal clear, but if you do have any questions, feel free. You've got access to the world's leading expert here, and so feel free to formulate questions. Email me any questions you have. We'll get the discussion going.